So in this lecture, I will discuss the transpose of a bounded linear operator. So the setup is the following. We have x and y Banach space, a map M from x to y, which is a bounded linear operator. And I recall you that we represent by x prime the dual of x. So this is the space of all bounded linear functionals L from x to the field K. In the same way, y prime will be the bounded linear functionals from y to K. And just to distinguish them, I will represent by L the bounded linear functional defined on y, and by M the bounded linear functionals defined on x. Now, you can compose, so if you have a bounded linear operator from x to y, you can compose this bounded linear operator with L to get Lm, which is now from x to k, which to a point x maps this point to L of m of x. Well, it is clear, and I leave it to you to check, that if L belongs to y prime, and m it's a fixed bounded linear operator, it won't change, then the composition Lm is a bounded linear functional from x to k. So Lm belongs to x prime. And so this composition maps bounded linear functional from y prime to a bounded linear functional from x prime. And I will represent this map by m prime. So m prime is a map from y prime to x prime, which associated to a bounded linear functional L, the bounded linear functional L of m. And this means that m prime of L, it's by definition L composed to m. So this defines a map, m prime. It's clear that this map it's linear. I claim also that this map it's bounded. So m prime will be a bounded linear operator from the normed linear space y prime to the normed linear space x prime. So let me show that m prime it's bounded. So again, I leave it to you to check that m prime is linear. So now let me show that m prime it's bounded. So I want to obtain a bound on that. I fix L in y prime and L of norm equal to 1. And I want to show that this object it's bounded by a constant 0 times the norm of L. So that this will prove that this operator m prime it's bounded. So m prime L is an element of x prime. Its norm as a bounded linear functional on x as an element of x prime, it's given by the supremum over all x in x, whose norm it's equal to 1, of m prime L at x. So this is, by definition, of the norm of an element of x prime. Now, by definition of m prime L, it's equal to Lm. So this is the supremum, and let me continue the computation over here. So m prime L, it's equal to Lm. So this is the supremum over x of L of mx. Now L, it's an element of y prime whose norm is equal to 1. So this is bounded. So we know that, well, this is an element of y. L, it's an element of y prime. So we know that this norm, it's bounded by the norm of L times the norm of mx. But the norm of L, we started from a bounded linear functional which has norm equal to 1. So this is 1. And what we get is that the norm of m prime L, it's bounded by the supremum over all x whose norm is equal to 1 of mx. And again, since m it's a bounded linear operator, this is bounded by the supremum over x of the norm of m times the norm of x. And this supremum is carried over all points x with norm equal to 1. So again, the norm of x is equal to 1. So this is equal to the norm of m. So we proved in this computation that for all L, so for all bounded linear functionals defined on y with norm equal to 1, m prime of L, it's bounded by m. So this tells us that this implies that the norm of m prime, so the conclusion is that the norm of m prime, which is equal to the supremum over all L with norm equal to 1, it's bounded by the norm of m. So we not only proved that m prime it's bounded, but we also proved that its norm it's bounded by the norm of m. So up to now, what we did is that we introduced this operator, this map, m prime, and we proved that this map it's linear and bounded. So actually, m prime, it's a bounded linear operator from y prime to x prime. So here is a summary of what we did up to now. We have two Banach spaces, x and y, and a bounded linear operator m from x to y. So we defined a bounded linear operator m prime from y prime to x prime by this equation, and we proved that the norm of m prime is bounded by the norm of m. So now let me consider an element of x prime, so bounded linear functional of x. I will represent by mx, so I'm introducing a new notation, so mx will be represented by xm. So this is an element of x prime, and this is an element of x. Sometimes it will be an element of y prime and an element of y. So now I have m prime L, which is a bounded linear functional on x. So if I take an element x in x, by my new notation, m prime L computed at x is written as x m prime L. So I'll never write x and x prime. The notation is clear. The context will make clear to which space these objects belong. Now, by definition, m prime L of x, by definition, is L of mx. Now, L, it's a bounded linear functional on y, so it's an element of y prime, and mx, it's an element of y. So with my notation, I can write this object as mx L. And therefore, I get an identity that x m prime L, it's equal to mx L, and this holds for all x in X and for all L in Y prime. And so this tells you that these transpose operators generalize the transpose of a matrix in finite linear algebra. So what we are doing here is that we are defining the transpose of some matrix M in this infinite dimensional context. So a lemma so I will not repeat the setup. We have this Banach space, a bounded linear operator M. We defined M prime in this way. What I claim is that the norm of M prime is actually equal to the norm of M. We already proved that the norm of M prime is bounded by the norm of M. So what we need to show now is that the norm of M is bounded by the norm of M prime. So the norm of M is this operator. So by definition, the norm of M it's equal to the supremum over all x with norm equal to 1 of the norm of mx. So now let's consider this object here. So x, it's an element of x, so mx, it's an element of y. So we have here an element of y. And we know that if y, it's an element of y, then its norm y, it's equal to the maximum, but I will write that as a supremum, over all L in y prime, L equal to 1 of L of y. So we proved that already, that if you take any element in a Banach space, then its norm, it's equal to the supremum of all bounded linear functionals L with norm equal to 1 of L of y. So what I will do here is just to apply this identity to mx. So this is the supremum for x of norm equal to 1. And now the supremum for all L in y prime, L of norm equal to 1 of L applied to mx. Now L applied to mx, we have the composition of L with m, and this is exactly m prime L. So this is the supremum over x, supremum over, okay, maybe L equal to 1 of m prime L of x. M prime L, it's an element of x prime. And this is the application of this element in x prime to x. Now, as an element of x prime, this expression, so m prime L, it's an element of x prime. So we know that if you have, let me write it maybe here, if you have an element m of x prime, m z, z an element of x, you know that this is bounded by the norm of m times the norm of z. So I will apply that to m prime L, which is equal to m, and to x, which is playing the role of z. So this is bounded by the same supremum, and here I have the norm of m prime L times the norm of x, but x has norm equal to 1. So this is bounded by the norm of m prime L. The supremum of x disappeared because x disappeared in this expression, and what remains is a supremum over all L with norm equal to 1. Now, we know that m prime is a bounded linear operator from y prime to x prime. It's bounded, so we know that its norm, the norm of the map of m prime to L, that this is bounded by the norm of m times the norm of L. So this expression here, it's bounded by the norm of m prime, the norm of L, but the norm of L, because L has a norm equal to 1, it's 1. And so this expression is actually bounded by the norm of m prime. So now what we get is that the norm of m, it's less or equal than the norm of m prime. And this is exactly what we wanted to prove. Since we already proved that the norm of m prime is bounded by the norm of m, we have indeed the identity. So now let me just make a remark. Suppose that we have two bounded operators, m1 and m2. So these are elements of Lxy. So these are two bounded linear operators from x to y. And let me take alpha in our field K. Alpha m1 plus m2, it's again an element, it's again a bounded linear operator from x to y. So yeah, it makes sense to consider the conjugate, the transpose of this bounded linear operator. And what I claim is that this transpose is actually alpha times the transpose of m1 plus m2 prime. And this is, clear, because to show that these two operators are the same, just consider L an element in y prime, apply alpha m1 plus m2 transpose to L. This, by definition, is L applied to alpha m1 composed. So by definition, this is the composition of L with alpha m1 plus m2. But by linearity of L, this is alpha L m1 plus L m2. So here we are using linearity of L. And now again, by definition of m1 prime and m2 prime, this expression, it's alpha m1 prime applied to L plus m2 prime applied to L. And therefore, we proved that this identity for all L in y prime, this means that this operator is actually equal to the operator alpha m1 prime plus m2 prime, and this is exactly what we wanted to prove. So we just proved that the transpose of a sum is the sum of the transpose. Now I want to connect m to m prime, and for that, let me recall that we represent by nm the null space of the operator m. So this is all points x in x, such that m of x it's equal to 0. And in the same way, we can define the null space of m prime which is, well, m prime applies to y prime, so these are all L in y prime, such that m prime of L prime it's equal to 0. Right? So this is the null space of m prime. So all bounded linear functionals in y prime such that m prime of L prime it's equal to 0. And in the same, so let me recall you what is the range of m. The range of m, and I will need some space. Well, this is just all points which are mapped. So this is, let me write it, it's easier, all mx such that x belongs to x, and this is therefore a subspace of y. Now, I don't know if you remember, but if I have a subspace, a linear subspace of y, I can define by a orthogonal, so this is actually a subspace of y prime made of all bounded linear functional defined on y, which send every element of y to 0. So this is a orthogonal is all elements L in y prime such that L of x it's equal to 0 for all x in A. So this is a linear subspace of y prime formed by all bounded linear functional which whose image in A vanish. So L of x it's equal to 0 for all x in A. So now I have here a subspace of y, which is a linear subspace, and my claim, my new lemma, so what I want to prove now is that if you take Rm, which is a linear subspace of y, you take Rm perp, which is now a subspace of y prime. This subspace of y prime coincides with the null space of M transpose. So I want to prove this identity, so I will erase all the blackboard and just keep the definitions to have more space in order to prove that lemma. So here I just recall you the definition of Nm prime, and here the one of Rm perp. So this is all L in y prime, so that L of z is equal to 0 for all z in the image of R, in the image of M. So we want to prove this identity, and I will start by proving that Rm perp it's included in Nm prime. So for that, I'll take an element L in Rm perp, and I'll show that it belongs to Nm prime. Since L belongs to Rm perp, this means that L of z is equal to 0 for all z in Rm, but any element in Rm can be written as mx for an x in x. So this is saying that L of m of x, that this is equal to 0 for all x in x. Right? It's L of z is equal to 0 for all z in Rm. So if you take an x in x, mx belongs to Rm, and therefore L of mx it's equal to 0. But now this is L composed to m applied at x. So by definition, this tells me that m prime of L of x, that this is equal to 0 for all x in x. M prime L, it's an element of x prime. And this element of x prime, let me call it m, it's such that mx is equal to 0 for all x in x. So this is telling me that m is equal to 0. Right? I have an element in x prime, so a bounded linear functional m, such that m of x is equal to 0 for all x. This is saying that m is equal to 0. So what we know is that m prime of L is equal to 0. So we prove that if L belongs to Rm perp, then m prime of L is equal to 0. But if m prime L is equal to 0, this means that L belongs to the null space of m prime, and therefore we just proved that Rm perp is included in the null space of m prime. Now let's prove the converse inequality. Let's prove that n m prime is included in Rm perp. So we'll do the same thing. Let's consider bounded linear functional L in n, the null space of m prime. So since it's in the null space, this means that m prime of L is equal to 0. M prime of L, recall, it's an element of x prime, so it's a bounded linear function in x. Saying that it's equal to 0 is to say that m prime L applied in x, that this is equal to 0 for all x in x. But now we can again use the definition of m prime. So this is saying that L of mx it's equal to 0 for all x in x. And this implies that L of z it's equal to 0 for all z in the range of m, right? All elements in the range of m can be written as mx. So since L of mx is equal to 0 for all x, this is saying that L of z is equal to 0 for all elements in the range of m, and therefore, by definition, this is saying that L belongs to Rm perp, and we just proved, therefore, that Nm prime is included in Rm perp, and therefore we have the identity, the lemma is proved. So now let me recall that Nm is the point, the null space of M. So these are all x in x such that M of x is equal M of x it's equal to 0. So the null space of M. And now, so this is a subspace of x. Now let me consider M prime. And let me represent by Rm prime the image of M prime. So this is the space of all M prime L, where L belongs to Y prime. So just the range of M prime. So the space of all M prime L for L in Y prime. And for that, I will now take the orthogonal of that. So I'm taking the range and the orthogonal of the range. Note that this object, since L it's in Y prime, M prime L it's in X prime, so this is a linear subspace of X prime. And when I have a linear subspace of X prime, I will represent by the perp of this subspace the points of x in x such that M of x it's equal to 0 for all M in Rm prime. So this is a subspace of x. Right? So since the range of M prime it's a subspace of X prime, I will define by Rm prime perp the subspace of X of all points X such that M of X is equal to 0 for all M in Rm prime, for all M in the range of M prime. And this, of course, it's a linear subspace of X. And my lemma is now that these two spaces are equal. So I claim that an M it's equal to Rm perp. M prime, sorry, perp. And so let's prove that by first showing the first inequality so that an M it's included in Rm prime perp. So let's take an element in an M. So this is a point X. So it's in the null space of M. So this means that M of X it's equal to 0. And if M of X it's equal to 0, it's clear that for any L in Y prime, right? So this is an element of Y and it's equal to 0. So this element of Y which is equal to 0, if I apply a bounded linear functional to this element, I get 0. So whatever L in Y prime, L of Mx, it's equal to 0. But again, by definition of M prime, this is M prime L of X. So this is an element of X prime. And what we are saying is that this element of X prime, well, applied to X, it's equal to 0. So, therefore, X belongs to, and since, well, and this is true for any L in Y prime. So this means that what I claim is that this implies that X belongs to Rm prime perp. To prove that X belongs to Rm prime perp, as I'm claiming, I have to show that Mx it's equal to 0 for all M in the range of M prime. So fix M in the range of M prime. This, since M belongs to the range of M prime, this means that M it's equal to M prime L for some L in Y prime. So there exists an L in Y prime such that M it's equal to M prime L. Well, but we proved that for all L in Y prime, M prime L, X, it's equal to 0. So indeed, M of X, so what we prove is that M of X, it's equal to 0 for all M in the range of M prime, and therefore, X indeed belongs to Rm prime perp. Okay, so let me repeat, just to make sure that it is clear. I fixed an X in the null space of M. This means that Mx it's equal to 0. Now I consider any L in Y prime, any bounded linear function in Y. So since this, which is the 0 point in Y, it's 0, L of it is 0. By definition, Lmx it's M prime L of X, and this is 0. M prime L it's a bounded linear functional of M, and now I claim that this identity gives me that X belongs indeed to this space. Why is that true? Well, to prove that X belongs to the range, the perp of the range of M prime, I have to show that for all M in Rm prime, M of X it's equal to 0. So take one M in Rm prime. Since it's in the range of M prime, this means that M it's equal to M prime L for some L in Y. take that L by this equation, M, which is M prime L of x, it's indeed equal to 0. So that proves that indeed for any M in the range of M prime, M of x it's equal to 0. And therefore, it means that x indeed belongs to the perp of the range of M prime. And this proves that first claim. So it remains to prove the converse inequality that this set is contained on that set. So the perp of Rm prime, it's a subset of x. So let's take an element x in Rm prime perp. So this, by definition, tells me, the definition of Rm prime tells me that m of x, it's equal to 0 for all m in the range of M prime. But the range of M prime, it's formed by all bounded linear functionals M prime of the form M prime L for L in Y prime. So this tells me that M prime L of x, it's equal to 0 for all L in Y prime. Now, by definition, M prime L, it's Lm. So this is Lm of x, which is 0 for all L in Y prime. But therefore, this is telling me that L of Mx, it's equal to 0 for all L in Y prime. So if this, if you have an element in Y such that L of Y is equal to 0 for all L in Y prime, it means that this element is equal to 0. Right? So if I have that L of Y for Y in Y, L of Y is equal to 0 for all L in Y prime, this implies that Y is equal to 0, because you can represent the norm of Y in terms of the absolute value of L of Y. So now I'm using this property to the point Mx. Since L of Mx is equal to 0 for all L in Y prime, this implies that Mx is equal to 0. And if Mx is equal to 0, it belongs to the null space of M. So this means that X belongs to the null space of M. And this is exactly what we wanted to prove. So that completes the proof of this lemma, the proof of this identity. So I want to conclude this lecture by considering a special case. So I'm assuming now that X is a Hilbert space and that I have a bounded linear operator from X to X. So I'm taking Y, in my previous context, set up Y equal to X, and X and Y a Hilbert space. And so remember that in Hilbert space, if I have an element L in X prime, then it can be represented through the scalar product. So there exists a Y in X such that L of X it's equal to X, Y. So we know that all bounded linear functional in a Hilbert space can be represented in this way. This is Rie's representation theorem, and this goes in the other direction. If I have Y in X, I can define by this identity a bounded linear functional. And I will represent this bounded linear functional by Ly. So all bounded linear functional are actually given by this expression, and this has already been proved. So in this context, in which I have this bounded linear operator, I can define, as before, the transpose of M prime, as a bounded linear operator from X prime to X by this identity. Now, let me define a new operator, m star. M star goes from x to x, and its definition, it's the following: m star of y, it's equal, so I fix y in x. Given that y, I have this bounded linear operator L of y, m star y, it's equal to m prime applied to Ly. So Ly, it's a bounded linear functional in x. M prime sends bounded linear functional in bounded linear function, so this is an element of x prime. So m star, it's sending elements from x to elements in x prime, but x prime, as you know, it's equal to x, so you can interpret that expression as x. So this is the definition of this operator m star. M star of y, it's given by m prime L of y, and I want to discuss a bit this operator m star. So we have x, which is now a Hilbert space. I have a bounded linear operator m defined in x, and from x to x, now I'm taking y equal to x, and we have seen that once this is settled, we can define the transpose of m prime, going from x prime to x prime. And now I want to define, well, and by this relation, now I want to define this operator, which maybe it wasn't clear in the previous blackboard, but now it's really an operator from x to x. And how do I define m star? So fix y in x. We have seen that I can define with this y a bounded linear functional L of y, which is so an element of x prime. Once I have this element of x prime, I apply m prime. So m prime gives me a new element in x prime. Now, since this is an element of x prime, and I have seen that all bounded linear functional can be represented by a unique point in x, I know that there exists a unique point in x, z, which I'm calling z, such that this bounded linear functional L of y, it's actually equal to L of z. And what I want to define m star of y, it's exactly this point z. So m star of y, it's indeed an element of x. It's this unique element z, which represents this bounded linear functional. So if I replace z by m star y, what I get is that this is equal to L m star y. And this is the definition of m star. M star y is the element of x such that m prime L of y, it's equal to L m star y. So this is the definition of m star. And now I claim that for all x, y in x, I have the following relation. M, so this is the scalar product of mx with y, that this is equal to x m star y. So m star, it's playing the adjoint of a matrix in finite linear algebra. Why is that so? So let me start with the right-hand side. So this is a point in x, and this can be represented as a bounded linear functional. So this expression is actually, so x m star of y is the bounded linear operator L m prime y applied to x. Right? Now recall this identity which we just proved, that L m star y, it's actually m prime L of y. So this is m prime L y applied to x. Well, this is a bounded linear functional defined in x, given by this identity. So, by definition of m prime, this is L of y applied to mx. And by, again, the definition of these bounded linear operator in Hilbert spaces, this is the scalar product of mx with y. So we have here the identity we just proved, the identity I wanted to prove. And this identity can also be used as a definition of m star. Right? You can define m star by this formula, saying that m star of y is the unique point for which this identity is true for all x. You can prove that there exists a unique m star y satisfying this identity, and that serves as an alternative definition of m star in the context of Hilbert spaces, which is the present case. And with that, I complete this lecture.